Okay, so this is part 3 of exam 2 review. I think I'm going to start you off with the NMR. Let's do that first. So then, which is the following? Oh, it's the wrong question. So it gives you the NMR, and then I'm giving you a roadmap. So the first thing I like to do with the roadmap is I like to see the formula. I think that helps a lot. So C5H12O2. I chose that one because it says HNMR is given on the previous page. So that's the formula for this. Oh wow, it's given up there. Sorry about that. Now I like to check like how many degrees of unsaturation there are. I check that especially because right now I know that we don't have a benzene ring because a benzene ring is from a 6 to 8 ppm, and we don't even reach up to 6. So we know that we don't have a benzene ring at all. So then I want to know if we even have unsaturated bonds, and the way that you would do that is you would do the formula for unsaturation. So your amount of carbons, which is 5, you multiply by 2. You always do that. Then you add 2. You always do that. And you get 12. Next thing you do is you subtract the amount of hydrogens that you have. I have 12 hydrogens. You always do this. You subtract the amount of hydrogens that you have. And I get 0. The next step would usually be to divide to see how many degrees of unsaturation you got. But when I divide 0 by 2, I get 0. So 0 degrees of unsaturation. 0 degrees unsat. So that means that these oxygens right here, we would usually have them in like carbon or something, but carbonyls have double bonds, and we know that that gives us a degree of unsaturation. And since we don't have any degrees of unsaturation, we know that we're gonna have to either put those on like an OH or an S ether group, stuff like that. Things like ways that you can put oxygens in your compound. Okay. So my next step, I like to start with the terminal carbons. So carbons with like 3 hydrogens on them. And I have 2 possible integrations of 3. So 3 possible terminal carbons. So I'm just going to start with any of them. So 3 hydrogens and a carbon. And you can only grow one way. That's why I call them terminal carbons. They're towards the end of a compound. So I think I'm going to go with this one first because it's a doublet. We know that it'll have only one neighbor because doublet means 2. 2 minus 1 is 1. So it only has one neighbor. Then I'm going to look for something on my NMR. I'm going to cross it out. I'm going to look for something on my NMR that has only an integration of 1. This right here has an integration of 1. Integration just means the number of hydrogens, right? So it says that it's a sextet, meaning 6. It has the integration or splitting pattern of 6. So 6 minus 1 is 5, and it should have 5 numbers. So I have a total of 1, 2, 3 on the right side, and I'm going to do 4, 5 on the left side. So this is now sextet, and we're good with that one. Next thing I'm going to look for is an integration of 2, because that's what we just wrote right here. I have 2 possible integrations of 2. I'm going to say it's a quartet, because that means I can keep growing it out. So if I just put a triplet, it means it would only have 2 hydrogen as a neighbor, and I already have 1 hydrogen on the right side, and if I had a second hydrogen on the left side, it would only have an integration of 1, and we have no more integrations of 1. We do have one, but we kind of know this is already, so we know is this one not the one. So I think it's this one right here. 2 hydrogens, so 1, 2 hydrogens with a quartet, and he has 3 neighbors. So I have a total of 1, try another carbon, 2, 3, and we're good with this one. Next thing I'm going to do is look for another integration of 2 hydrogens. The last one we have is this one right here, integration of 2. And it says it's a triplet, meaning it has 3 minus 1, 2 neighbors. So then if I just look at this right here, I have 1, 2 neighbors on the right side. I can't have any more, so I'm going to cut it off here. That's already one piece of our puzzle. This is one piece of our puzzle, and notice how this carbon is missing a 4th bond, so this is something that we might be able to attach something to, right? Then 2 possible attachment sites. And we already crossed out a lot of our signals. I see one other thing that I can do. So I have another terminal carbon, which has 3 hydrogens on it. And it's a singlet, meaning it has no neighbors. So that's another piece of the puzzle. The last thing that I see is this right here. So it's a singlet. It's a very far down field. and it's only one hydrogen. So when I see something like that, I immediately think hydroxyl group. So hydroxyl group is being cut off by the oxygen with only one hydrogen, so it has no neighbors and everything. And it has no neighbors and everything, so this should be what that is. We have another piece of our puzzle. All these puzzle pieces are things we can attach them to. The only thing we notice is, well, let me count. So I have 1, 2, 3, 4, 5 carbons, so good with this. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens, 1 oxygen, and I'm missing 1 more oxygen, which is making me think that I'm going to have an ether group. Ether just means that oxygen in between two possible, like two substituents, two random things. And so, okay, I'm going to make this another piece of my puzzle. Now all we can do here is put things together. So I would probably look at how downfield everything is. So this sextet right here is the most down, or second most downfield next to this one right here. So I think I'm gonna put my OH right here. Yeah, so that's good. We got rid of one of our puzzle pieces. The second thing I can do is, I know I can't attach this site right here because it would make this group a 1, 2, 3, 4, 5, a sextet. So we would have 2 sextets, and we don't have 2 sextets in our entire NMR. So we can't attach those together. So what I'm thinking is I'm going to attach this right here. I'll do that. Awesome. And attach this group to this. Yeah. And so that'll explain why this 3 hydrogen singlet is more downfield than a lot like the quartets and everything. So how downfield everything else is, okay, well, when I look at the NMR, I don't really look at how downfield everything is until I have all my puzzle pieces. So I think after you have your puzzle pieces together, after you have all your atoms together, you know what kinds of functional groups are going to be on your compound. That's when you start determining where everything goes based on how downfield everything is. But yes, this should be our compound for the NMR. Let me make it look pretty. 1, 2, 3. Oops. 1, 2, 3, 4, 5. So, and on carbon number 4, I have an OH. That's what I'm going to draw in my NMR box. There we go. All right, so I'm going to go to the right side. So we have a chromate. Chromates oxidize. They're very good oxidizing agents. The only thing that we can oxidize here is the alcohol. So oxidizing just means that we're going to make more bonds between a carbon in this case and electronegative atom like oxygen. So increasing those bonds, meanwhile decreasing any carbon hydrogen bonds or OH bonds, like how we do right here. So what we're going to oxidize is going to be our alcohol. Oh, I'm sorry. Yeah, only the carbon hydrogen bonds. So notice how right here we have a carbon hydrogen bond, but when I oxidize it and put a double bond in that place, I no longer have that carbon hydrogen bond, meaning we are oxidizing, minimizing CH bonds and increasing C carbon bonds to oxygen. All right. I think I'm gonna go to box B now. Okay, so on B, it says that B gives the silver mirror test in the Tollens reagent. Gives a silver mirror in the Tollens reagent, meaning it's positive, so like positive test. For toluenes, if you have a positive test, it means that you have an aldehyde. Aldehyde. So that means that B is going to be an aldehyde. Let me draw an example of aldehyde because I'm about to show you something else like this. So in box B, we have an aldehyde. And we're going backwards. Look at how the arrow is going. So it's saying that if we react this aldehyde with CH3, MgBr, and H2O, I'm going to get something like this. RH, methyl group, and an OH, which is exactly what we got right here. So what I think I'm going to do is I'm going to keep the left side the same, and I'm going to change this carbon right here into an aldehyde. Yeah. Yeah, so notice how this group right here is the same as this group right here. Then, again, just to make sure that I'm right, I'm going to count on my carbons. So 1, 2, 3, 4. Good there. 4 carbons. We have 3 plus 2 plus 2 plus 1. And that's a total of 8. So good there. And you have a total of 2 oxygens. So we're good. Then I'm going to go to the middle one because I think that'll help me figure out this next one. So a ratio of 3 to 2 on your mass spec is going to be chlorine, right? And a ratio of 1 to 1 is going to be bromine. So right now we have a ratio of 3 to 1. We know we're going to have chlorine in here. We don't know what kind of functional group we'll have it in or if we'll just have it by itself. But I know that this is going to be an acid chloride right here. Acid chloride. Because of this IR spectra. So anything around 1810 inverse centimeters is going to be an acid chloride. So then, okay, those are all my hints for D, but I also see that we have dibol. We know that dibol creates aldehydes, and it often uses like acid chloride. So in the place of my aldehyde right here, I think I'm going to use everything the same and put in my acid chloride. Cool. Yeah, we should be good like that. Okay. Next thing I'm going to do, I'm going to go down to this box. So we have lithium aluminum hydride, which is a strong reducing agent. Strong reducing agent. There you go. So then it's going to attack as many times as it can. It'll usually attack 2 times when we have a good leaving group. And in this case, we have an acid chloride, so we have a good leaving group. So then instead of this acid chloride, I know that I'm going to turn into a primary alcohol. Nothing else but that changes. Primary alcohol, count your carbons to make sure you're good. For total of 3, 2, 2, 2, 1. This is me counting my carbons. Am I missing something? Oh yeah, I'm good. So I have a total of 10 hydrogens and a total of 2 oxygens. So this should be our right compound. And then just to check myself, I can use the PCC. So PCC turns alcohols into carbonyl groups. And that's exactly what happened right here. So this alcohol right here is going to turn into a carbonyl group and have the leftover hydrogen as well. So we're good with that one. And we have our last one. So we're reacting this acid chloride with another organometallic in excess. So we know that we're going to be using it more than once, especially because we have a good leaving group. So then we're going to add this methyl group 2 times to this acid chloride right here. So draw everything the same. 1, 2, 3, 4. And to the 4th carbon, 1, 2, 3, 4. I'm going to be adding 2 new methyl groups. One to kick off my chlorine, another to keep attacking, and I'll have a leftover OH group. And then just to make sure I'm good with that, I'm gonna count carbons 1, 2, 3, 4, 5, 6. And that's a 6, I believe. Yeah. I'm gonna count my hydrogens. 3, 2, 2, 3, 3. This is 6, 8, 10, 13, 14. Yeah, we're good. Good with the hydrogens, good with the carbons, and we have 2 alcohol, 2 OHs. I mean, 2 oxygens. So we're good with that. So we did roadmap and NMR. Next thing I want to do, I'm going to do the ranking one. So rank the following carbonyl carbons. Which one will react faster in the Grignard's reaction when reacted with benzyl magnesium bromide? So 1 being the slowest, 5 being the fastest. This one is one that I got on my exam. This one was tricky though. So it's asking for a Grignard's reaction. So anything other than Grignard's is going to be considered like a no reaction. So here you pretty much just have to rank in order of better leading group. And we know that just by looking at all of our options, we have ester and chloride. Those are very good leading. Ester and chloride. Those are very good leading groups. So one of these is going to be our fastest one. And we know that just by the ranking system, chloride is a better leading group. So this one's going to lead faster. Again, the reason is because the chloride is pulling away more electron density from the carbonyl carbon, making this carbonyl carbon more electrophilic, making it easier for something like the Grignards to come and attack. So this will be our 4th one. And then I think I'll start talking about, no, I'll go for the 3rd one. So I feel like from here, we would think this would be our next one, the 3rd one. But remember how we were talking about carboxylic acids and how magnesium, of how Grignard's reagent can count as a base. So something like this is not going to undergo a Grignard's reagent. It's going to undergo an acid-base reaction. So it'll give you a product like this. Actually, this is only 1 carbon, so it'll give you CH4. Acetate and positive charge on magnesium bromide. Those are the products that you would get from this type of reaction. So notice how we have an acid, so from the carboxylic acid, and it undergoes acid-base reaction. So then this is going to be our slowest just because it's not undergoing Grignard's reaction, how we were asking it to. Okay. From there, I'm going to ask about 3. So we have a plain ketone right here, and we have an aldehyde as our second option. Grignard's reagents like to attack very electrophilic carbonyl carbons. So here we're going to be looking at the 2 substituents on our carbonyl group. So we have 2 carbons right here donating electron density because they donate electron density through the inductive effect, right? Whereas on the aldehyde, you only have 1 donating electron density. Again, we don't want electron density on our carbonyl carbon because that makes it more rich in electron density. So we want it to be electrophilic and we don't want it to be rich in electron density. So we're going to prefer the aldehyde over the ketone. So the aldehyde is going to react faster than the ketone group. Okay, now I'm going to do the bases. I think this is one of the more difficult ones for me because I like sucked at acids and bases for a long time. But I think as you keep practicing it, you become better at it. So here's what we have for this. Which of the following bases will be strong enough to deprotonate the following? Place the letters underneath the compound. So these are all our bases, and they're asking which of these bases are strong enough to deprotonate these different groups, right? Okay. So the first thing I'm going to do is ask for the pKa's of each one of them, so A through F. And the reason that I ask for the pKa's of those is because pKa of the conjugate acid determines the strength of your base. pKa of conjugate acid determines strength of base. So again, remember how a strong base equals a weak acid, or a strong acid equals a weak base. So pKa of a conjugate acid determines the strength of it. So then what we're going to do for each of these is give the pKa's. And these are ones that you should obviously memorize for this upcoming test. Let me give you all the pKa's that I know. Here. The first one, the conjugate acid of NH2 is NH3. The pKa of NH3 is 38. Let me check myself. No, yeah, it should be 38. Yeah. And then conjugate base of acetate is acetic acid. pKa of acetic acid is 4.8. Then we have conjugate base of ethanol. I don't know, but it's ethanol, right? So conjugate acid is ethanol. And the pKa of ethanol is going to be 60. I want to do this one just because it's close to ethanol. So we have a hydroxide group. The conjugate acid is H2O. We know that the pKa of H2O is 15.7, around 15.7. Look at NH3. Conjugate acid is NH4 plus. pKa of NH4 plus is 9.4. And we have carbon-carbon triple bond. Carbon-carbon triple bond is 25. Yeah. Normal carbon-carbon triple bond, both protonated, is 25. pKa of 25. So let me box these in so I don't get confused. Okay. And so I'm gonna write these down here just so, again, I can just see this all as one. Okay, so we always had trouble with this on our session. So low pKa equals strong acid, right? High pKa equals strong base. I need these bases to protonate these acids. So that means the pKa's of these bases have to be higher than the pKa's of these acids, again, because high pKa equals stronger base. Okay, so then what I'm going to do is any pKa higher than 18 is going to be able to deprotonate this group right here. So now let me just look through them. 38 is way higher, so A is one of them that can deprotonate. 4.8 is not higher, 16 is not higher, 25 is higher, so D is another base that can deprotonate this group right here. And I think those are the only ones. Yeah, we're good with those. We're doing the same thing with this one right here. The parachloro something all. I don't know. I tried. Okay, so then this is the PKA. Anything larger than 9.4 is going to be able to deprotonate this proton right here. So then I have for sure A will be able to deprotonate, not B. C will be able to. D will be able to. And if they have equivalent pKa's, they're going to be in like equilibrium and they're going to be deprotonating and protonating. So you can count the ones that are the same as being able to deprotonate. And then last one, F is able to as well. Then for this last one with a pKa of 3.4, I believe all of them are above 3.4, so all can deprotonate. And we're good with those. Last thing I'm going to do is I'm going to do nomenclature. I'm so bad at nomenclature. Okay. So for this first one, we're going to be naming a ketone. For the second one, we're going to need carboxylic acid. And then I'm going to give you some of the structures that you should know in case they ask you to memorize any for your test, right? So, okay. So for my ketone, I'm going to find my longest chain and I'm going to number it in ways where my higher number will have the more amount of substituents on it. Higher number meaning like closer to 1. So I'll number it like this: 1, 2, 3, 4, 5. Notice how I numbered it in this way instead of going from 1 to like that onwards, because I have 2 methyl substituents on 2, so higher amount of substituents on a greater number. So again, 2 methyl groups, so 2 methyls on carbon 2, and I have 1 methyl on carbon 4. And those are pretty much the only things that we're going to have to name other than the ending part of our ketone, right? So I'm going to do trimethyl. Actually, no, starts with a number. 2, 2, 4, trimethyl, because we have 3 methyl groups. Penta, we have 1, 2, 3, 4, 5. It's the longest chain. I'm going to put my dash in between, and I'm going to put 3, 2, 2, 4, trimethyl, penta, 3, or you can do 2, 2, 4, trimethyl, 3, pentanol. I think those are the 2 possible ways that you can do it. So we're good with that. Then we have our carboxylic acid. And for your carboxylic acids, for sure, you start number 1 at your carbonyl carbon. So 1, 2, 3, and you go for the longest, 4, 5. So it's going to be a penta. It's going to be a pentagroup. And instead of the ane part, pentane, it's going to be pentanoic acid. That's the suffix you add for your carboxylic acids. What else? Okay, now I'm going to name my substituents. So I have 3, 3 dimethyl. I think we're good. 3, 3 dimethyl pentanoic acid. There we go. Jeez, that took a lot out of me. Okay. Now I'm going to do some of the common ones that you're going to see. I have a list of them. So these are the ones that they can be like, oh, what is this? What's the name of this? So nitrogen with 1, 2, 3, 4. So butyl groups. Okay. 2, 3, 4. Plus, and we have fluorine plus 5. So the name of this one is going to be tart for 4, butyl for the amount of carbons that I was adding to each one of them, tart butyl ammonium. Again, ammonia is like an amine group, and the ium means that you have a positive charge on it. So ammonium, and then last one, fluoride for the anion, for the ion that's making this neutral. So tart butyl ammonium fluoride, also known as TBAF. There you go. Another one is going to be this one. This is tributyl for this group right here. It's tributyl. Dimethyl for the two methyl groups right here. Cellule. And I think the cellule is just the silica right here. So then the code name for this one is the TBDMSCl. And that's another one that we should memorize for sure. Another one that I'm going to give you is, I think this is the one that was on my test. Diisobutyl. So di meaning two, and you have two isobutyl groups. Diisobutyl, aluminum hydride. I'm missing something. Yeah, I was just missing this hydrogen right here. So diisobutyl aluminum hydride, also known as dibol H. I'll give you one more. Not one more. I got two more for you. Nitrogen. And this one is imidazole, which is one of the solvents that we use for one of our protecting groups. And I'm going to give you one more. This one is one that you're going to see very often. Oops. You're going to see this very often in biochem. And the name of this is NADH. Yeah, I think those are all the ones that you're gonna have to remember. Go over your nomenclature before the test just a little bit. Those are easy like points, and I know like I'm really bad at that, and that's just because it's something I concentrated on a lot. I concentrated on more of the tougher subjects, like all of these and everything, and then I would leave the nomenclature off for the last point, so that right before the test I'd know how to do it, but it wouldn't take up a lot of my storage, right? So yeah. I think we're done with this worksheet. And if you guys need help on anything else, I'll ask you guys, and I can probably post more videos on that. So, yeah. Thank you guys.